Here we're going to look at an interesting infinite product involving the tangent function. So we want to look at the product as n goes from 3 to infinity of 1 minus tangent to the fourth of pi over 2 to the n. We're going to use 3 tools in order to evaluate this product, which we'll prove just for completeness of the video. So the first tool is the double angle formula for the tangent function. It says that tangent of 2 theta equals 2 tangent theta over 1 minus tangent squared theta. Okay, so let's see how this one goes. So we're going to start with Euler's formula, which says that e to the I theta equals cosine theta plus I sine theta. And then we'll square this, but we'll square it thinking about it 2 different ways. So we'll look at e to the I 2 theta versus e to the I theta quantity squared. So notice looking at it like e to the I 2 theta, that gives us cosine of 2 theta plus I sine of 2 theta. But then looking at it as e to the I theta quantity squared, that gives us cosine theta plus I sine theta quantity squared. Now the general trick is you want to expand the right-hand side and then extract the real and imaginary parts to build these trig identities, and that's exactly what we're going to do. Okay, so let's go ahead and expand this right-hand side. So notice that's going to give us cosine squared theta minus sine squared theta. So that's the real part because we have cosine times cosine and then I sine times I sine, so that gives us minus 1 times sine. And then let's see what we have for the imaginary part. So we'll have I times, but then we've got just the cross terms from squaring that binomial. So it'll be 2 cos theta sine theta. Good. So that's what cosine 2 theta plus I sine 2 theta is. So that immediately gives us the double angle formulas for cosine and sine. Notice that cosine of 2 theta will be equal to cosine squared minus sine squared. And notice that sine 2 theta will be given by 2 cosine times sine just by extracting real and imaginary parts. But we're looking for tangent of 2 theta. So we can get that by taking this equation and then dividing it by cosine of 2 theta because we know sine over cosine is tangent. So let's go ahead and do that. Take this entire equation and do 1 over cos 2 theta. So let's see. That's going to give us 1 plus I times tangent 2 theta. So that's what happens to the left-hand side. And then on the right-hand side, we have cosine squared theta minus sine squared theta over, let's see, cosine 2 theta. And then plus I 2 cosine theta sine theta. And this is all over cos 2 theta. And so now notice that we don't really care about the real part of this equation, given that the imaginary part of the left-hand side is exactly what we're looking for. In other words, it's tangent 2 theta. So that means we can just go ahead and get rid of the real part of the left-hand side and the real part of the right-hand side. And that gives us this nice equation, which is tangent 2 theta equals 2 cosine theta sine theta over cosine 2 theta. But that right-hand side is not written in terms of just cosine theta and sine theta. We still have that cosine 2 theta built in there, and we want to get rid of that. But we can get rid of that by using this identity that we have from the last step in this problem, and that's cosine 2 theta is cosine squared minus sine squared. So we can insert this guy into this. But we'll insert it using this form, this cosine squared minus sine squared form. Okay, so let's see. That's going to give us tangent 2 theta equals 2 cos theta sine theta over, so now we can rewrite this as cos squared theta minus sine squared theta. But now we might want to divide the numerator and the denominator by cosine squared to put it in terms of tangent. So let's go ahead and do that. So we'll hit the numerator and the denominator by 1 over cos squared. So let's see. That's going to leave us with 2 times tangent in the numerator. And that's because one of these cosines cancels this cosine. And then one of them is left underneath the sine to make tangent. And now we have cosine squared over cosine squared, which is 1, minus sine squared over cosine squared, which is tangent squared. So we have 1 minus tangent squared theta. But notice this tangent 2 theta equals 2 tan theta over 1 minus tan squared theta is exactly our first tool. And now we're ready to look at this second identity. So that says that 1 minus tangent squared over 1 plus tangent squared equals 1/2 times sine 4 theta over sine 2 theta. So we're going to actually use some of our intermediate calculations from the last board. We're going to use this cosine squared minus sine squared equals cosine 2t. And then we'll use 2 cosine t sine t equals sine 2t, where we might have to play with that t. Maybe it'll be theta or maybe it'll be 2 theta, kind of depending on exactly what we need for this object right here. Okay, so let's go ahead and look at the left-hand side of this. So we've got 1 minus tangent squared theta over 1 plus tangent squared theta. Great. But I'm going to go ahead and put this in terms of sines and cosines. So that's going to give me 1 minus sine squared theta over cos squared theta over 1 plus sine squared theta over cos squared theta. And now that just screams out to multiply the numerator and the denominator by cosine squared theta to make some simplification. So let's go ahead and do that. So we'll hit the denominator and the numerator by cosine squared theta. So let's see what that gives us. So in the numerator, we'll get cosine theta squared minus sine squared theta. And then in the denominator, we'll get cosine squared theta plus sine squared theta. So we've got cosine squared theta plus sine squared theta. Great. But now by the Pythagorean identity for cosine and sine, we know that the denominator is equal to 1. But then by the double angle formula for cosine, which we saw on the last board, we know the numerator is equal to cosine 2 theta. So this guy right here is equal to cosine 2 theta. Good. Now we want to look at this cosine 2 theta and maybe put it inside of this equation right here where t is equal to 2 theta. So maybe let's just go ahead and bring this thing down here and look at what this double angle formula for sine looks like if we set t equal to 2 theta. So that's going to give us 2 cosine of 2 theta times sine of 2 theta equals sine of 4 theta. Great. But now notice if we divide out to isolate cosine of 2 theta on the left-hand side, we'll get exactly what we want. And so we have to divide out a 2 and a sine 2 theta, and that tells us that this is equal to sine 4 theta over sine 2 theta, and that's also divided by 2, but I'll just bring this 1/2 out. Okay, so we've established this second formula. And now we're ready to establish our third tool, which is this limit. So let's go ahead and write the left-hand side of this down. So we've got this limit as n goes to infinity of 2 to the n and then sine of pi over 2 to the n. Great. So what I want to do is do a change of variables to change this into a more common limit. And that change of variables I'll do is I will set x equal to pi over 2 to the n. Great. But now notice as the limit n goes to infinity, x is going to tend towards 0. So when I change this to a limit with respect to x, x is going to tend towards 0. And now we also maybe want to solve this for 2 to the n because that also shows up in the limit. So let's go ahead and do that. That's pretty easy. We've got 2 to the n equals pi over x. Great. So now we can rewrite this limit using our substitution. So that's going to give me this limit, but now x is approaching 0 of, so we've got 2 to the n. I'm going to write that as pi over x. And then I have a sine of pi over 2 to the n, but that's just sine of x. And so I can take that pi out front because it's a constant. So that gives me pi, and then the limit as x approaches 0 of sine x over x. Now that's a pretty common limit from Calculus 1. You might remember that that limit is equal to 1, and you can do a really nice geometric argument for that, or we could just apply L'Hopital's rule, noticing that this is an indeterminate form of type 0 over 0. So applying L'Hopital's rule, that gives us this pi times the limit x goes to 0 of cos x over 1, taking the derivative of the numerator and the denominator. But now cosine of 0 is 1, so that gives us that this limit value is pi, which that's exactly what we wanted to show. Okay, so now that we've got all of our tools developed, we're ready to tackle this product. So we're going to use the definition of an infinite product as the limit of the partial products. So I'm going to go ahead and write this as the limit of capital N tending towards infinity of the product of little n going from 3 to capital N. And then I'm also going to set theta sub k equal to pi over 2 to the k just for simplicity. And notice that that implies that 2 theta k equals theta k minus 1 and 4 theta k is equal to theta k minus 2. We'll probably need that as we move forward. Okay, so now the next thing that I want to do is go ahead and factor this thing right here. So notice I've got 1 minus tangent to the 4th, which means I can factor it like 1 minus tangent squared and 1 plus tangent squared. So let's do that. So we've got 1 minus tangent squared theta n. I've replaced my pi over 2n with theta n. And then I next have 1 plus tangent squared theta n. Okay, good. Now we want to look at our identities. So these identities are meant to build this into a telescoping product. So let's zero in on this second identity first. Notice it's 1 minus tangent squared over 1 plus tangent squared. Well, here we have a 1 plus tangent squared in the denominator. So we can build out the rest of this identity by dividing by 1 minus tangent squared. In other words, putting a new one in the denominator, which means we need to introduce a new one into the numerator, and we can do that by squaring this thing right here. Okay, so now let's also look at our first identity, which has a 1 minus tangent squared in the numerator. So we need to pair that with a 2 tangent theta in the denominator. So we can do that by putting 2 tangent theta n in the denominator to be grouped with this 1 minus tangent squared theta n in the numerator. But notice that's being squared, and so in order to counteract the fact that we've introduced a 4 tangent squared into the denominator, I'm going to multiply this whole thing by 4 tangent squared theta n in the numerator. And now I haven't changed anything at all. Okay, good. So now the next thing that I want to use is the second identity to rewrite this term, and then the first identity to rewrite this term, keeping in mind that it's being squared and that we have the reciprocal of these two identities. So that's going to give us this limit as capital N goes to infinity. Now we have this product of n going from 3 to capital N. So this blue box is governed by this blue identity, but we have the reciprocal of it. So notice that's going to give us a tangent squared 2 theta n in the denominator. And so I've got that 4 tangent squared theta n from over there. So I'm going to bring that here. So 4 tangent squared theta n. And then from this blue box, I have tangent squared 2 theta n. Great. But now this red box is exactly the reciprocal of this red identity right here. So now I can multiply this by 2, and now I have sine of 2 theta n over sine of 4 theta n. Good. So notice that's going to give us this limit as capital N goes to infinity of this product, little n going from 3 to capital N. Now I can bring an 8 in front of the whole thing. And now I have tangent squared theta n in the numerator. And now I have tangent squared theta 2 theta n in the denominator. But notice 2 theta n will be theta n minus 1. But that's a really nice substitution because that builds our telescoping action. So I can rewrite this as tangent squared theta n minus 1. So just to reiterate, this is the replacement that I've just made. Okay, good. Now I can do the same kind of thing in the next bit, but I'll do 4 theta n and 2 theta n. So notice that's going to give me sine of theta n minus 1 and sine of theta n minus 2. Good. Now the next thing that I want to do is expand this product, maybe write out the first two terms and the last two terms so that we can have some sort of idea for how this will telescope. So this is going to be equal to the limit. This capital N is tending towards infinity. Now let's see the first term. So that's my n equals 3 term. So I have an 8. So 8 is going to be part of all of the terms. So I've got 8, and then I have tangent squared theta 3 over tangent squared theta 2. And then I have sine theta 2 over sine theta 1. Good. So like I said, that is my n equals 3 term. In other words, the first term of this product. So now let's look at the n equals 4 term. So my n equals 4 term, I'll still have another 8, and then I'll have a tangent squared theta 4 over tangent squared theta 3. And then I have a sine theta 3 over sine theta 2. Good. And now I have dot, dot, dot. Now let's do maybe the n equals n minus 1 term. So I'll put that down here. So the n equals capital N minus 1 term. So in other words, everywhere I see an n, I'm going to put an n minus 1. So that's going to give me an 8. And then I have tangent squared theta capital N minus 1 over tangent squared theta capital N minus 2. And then I have the same kind of thing with sine. So this is the sine capital theta n minus 1 over sine theta, sorry, that should be n minus 2 in the numerator and theta n minus 3 in the denominator. Okay, good. And then finally, we have the very last term, which will be the little n equals capital N term. And that's going to give us an 8 and then a tangent squared theta n over tangent squared theta n minus 1. And then we have sine theta n minus 1 over sine theta n minus 2. Good. And now let's see what seems to cancel as we move through this. So notice we've got this sine theta 2, which will cancel this sine theta 2. And then likewise, this sine theta 3 will be canceled by something that's happening in the future. Then let's see what else we have. So we've got a tangent squared theta 3, which will cancel the tangent squared theta 3 here. Good. And then we also have a tangent squared theta 4, which will cancel a tangent squared theta 4 in the future. Okay, great. And then now let's see what's happening at the end. So here we have a sine theta n minus 2, which is going to cancel a sine theta n minus 2 there. Then we have a sine theta n minus 3, which will be canceled by something in the past. And then let's see what else. We have a tangent theta n minus 1, which will cancel this tangent theta n minus 1 happening in the future. And then this thing will get canceled by something that's happening previously. And now let's see, I think that's all that's left. And so what's left is we have all of these 8s, and then we have this tangent squared theta 2 right here, this sine theta 1 right here, and then this tangent squared theta n and sine theta n minus 1 over there. Okay, so I'm going to go ahead and summarize that up here, and then we're almost done. So in the last board, we saw that our infinite product was going to telescope down to the following form. So notice we've got 8 to the n minus 3, and that's because we're starting at n equals 3, so our partial product, 3 to n, had exactly n minus 3 terms. So that explains the exponent on the 8. And then everything else telescoped down to tangent squared theta n times sine theta n minus 1 over tangent squared theta 2 times sine theta 1, where theta k was equal to pi over 2 to the k. Now, I want to notice we've got some special values here. Notice that theta 1 is equal to pi over 2, and theta 2 is equal to pi over 4. But that's actually extremely helpful because we know that the sine of pi over 2 is equal to 1. And we know the tangent of pi over 4 is equal to 1. So that allows us to simplify those two nicely. Now what I want to do is rewrite this using my definition for theta k and by expanding the tangent into sine squared over cosine squared. So that's going to give me the following. And another thing that I want to do is bring a 1 over 8 cubed out front. So I've got 1 over 8 cubed out front of everything. Now I have this limit as capital N is going to infinity of 8 to the n. And now I'm going to have sine squared pi over 2 to the n, just rewriting my theta n, over cos squared pi over 2 to the n. And then that's going to be multiplied by sine squared pi over 2 to the n minus 1. Good. Now notice I've got a limit which is composed of parts that look like my third tool here. But in order to use this third tool, I need this exponent of the 2 that's outside of the sign to be exactly the same as the exponent of the 2 that is inside the sign. And so I can tweak this 8 to the n to make that work. So notice I can rewrite this as 2 to the n squared. So that's going to be grouped with this term. And then after that, I have the following. So I will have 2 times 2 to the n minus 1. Great. And then this 2 to the n minus 1 will be grouped with this term. And then this 2 can be canceled with this 1 over 8 cubed outside in the future. Okay, so now let's rewrite this. So we've got 2. I'll bring that out front. And then I have 8 cubed, but notice that's the same thing as 2 to the 6. And now we have this limit as n goes to infinity of, so this is going to be 2n quantity squared times sine squared of pi over 2n. So I'm going to write that as 2 to the n sine pi over 2 to the n, and then the quantity squared. And also I'm going to break this apart into separate limits, and I can do that because I know all of these limits exist. And then the next thing is going to be, this is multiplied by the limit as n goes to infinity of 2 to the n minus 1 times sine of pi over 2 to the n minus 1. And that sign shouldn't have been squared. And then finally, I have the limit as capital N goes to infinity of 1 over cosine pi over 2 to the n. Great. So let's see what we get for each of those. So 2 over 2 to the 6th, that's 1 over 2 to the 5th. So that's 1 over 32. And then this guy is going to become pi squared, given the fact that it's exactly this limit squared. So I can take this and replace it with pi squared. This limit is going to be pi because exactly this limit, just like re-indexed a little bit. And then since cosine of 0 is 1, this is tending towards 1 over 1, which is 1. So in the end, we have 1 over 32 times pi squared times pi. In other words, we have 1 over 32 times pi cubed. In other words, pi cubed over 32. And that's our final answer. And that's a good place to stop.